Hello humans, since I asked you whether you want a new video on Vax Recodes or a chill gaming live stream, you chose the video, so you'll get a video. Today I wanted to talk to you about a bit about the plugin system, how it actually works, and I believe one of the most fun parts of the plugin system, which is the hooks. This file that you're seeing right now is the entire hook system, and I would say it's the most used part of the plugin system in Hyprland, and yet it's the part that the most developers that see Hyprland source treat as the absolute biggest atrocity that you could ever make. Generally it's one of these things that is like really cool, really useful, but extremely dangerous, and something that Rust or Python wouldn't ever allow you to do unless you, I don't know, used some magic hacks to get around every single safety feature that the languages have. So today I wanted to talk a bit about how it works and what it's all about. So if you take a look in the plugin API header, which is where you should head to if you want to write plugins, you'll see that you can create a function hook. And it creates a trampoline function hook to an internal Hyprland function. Obviously warning that they're not guaranteed any API stability. What does it mean? For example, when you're a plugin, and let's say you want to go to the animation manager and, for example, change what happens when I don't know, someone gets all Bayesiers, or whether schedule take. This is actually a pretty bad example. Let me find a more reasonable example. Here, compositor should have. Okay, let's say that you're making a plugin that changes how workspace visibility works, right? There is a function inside Hyprland that says, is workspace visible? Basically checks if a workspace is active on any monitor or if it's an active special workspace on any monitor. But let's say you have a plugin that changes how that works. Well, you would want this function to reflect which your plugin changes, right? But obviously, since you're making a plugin, you cannot physically distribute a patch and be like, oh, hey guys, can you patch Hyprland alongside with my plugin? That's not how plugins work. So what you can do is make a function hook. And a function hook will basically take this function, and every time Hyprland or a different plugin calls this function, it will instead call your function. And you might first think, well, how does it work when every plugin, pulls a random place in memory? How can that change, right? And that's what I want to show you how to do that today. Generally, I want to tell you that this is probably a thing that you shouldn't do. It's extremely dangerous, and not dangerous in the sense of, I don't know, the FBI is going to come after you. No, it's just extremely unsafe, and very, very powerful. The reason why I added it is because I don't want to make the API so huge that it will be a pain to maintain. So I can kind of offload that pain into people that maintain plugins, so they have to make their own stuff. So the most important part about this entire code is how functions work in actual assembly. I'm gonna pull up Kate here to demonstrate my point. So when you compile your code, it gets compiled into machine instructions. For example, I don't know, move ECX, probably should be R because we're 60, right? This will copy what is in the RCX register into the RAX, or the other way around. Always get them the other way around. And your computer only understands these instructions. This is a readable way, but technically they're represented as zeros and ones. And every single program is just tons and tons and tons of different instructions, right? You could have, I don't know, add EAX 2, right? or sub RAX5. So those are different registers. You can also, I don't know, load an effective address of some place, I don't know, 0x35 of I don't know, RAX into RBX or whatever. You have a lot of functions that just kind of do extremely simple things. And every function is just a ton of those instructions. So at some point in memory, let's say this is our point 3. Kate here gives us the line number, but let's say this is the memory address 3. Obviously it won't be like that because every instruction is more than 1 byte. Well, almost all instructions are more than 1 byte, so it would be like 3 and then like 8 and then like whatever. But let's simplify it and say that this is address 3, this is address 4. So somewhere in the code is something like, I don't know, call 3, right? And this is the place where our program calls the function. So it's like, hey, go to address 3 and start executing from there. And then at the end of the function, you will get a ret, which will basically come back to where it was called from. Pretty sure. Now, what a trampoline hook does is you take the beginning of this function and you override it. So first of all, you see that the computer will just go to address 3 and start executing whatever is there. So what a trampoline hook does is it figures out the first few instructions, it cuts them, and then it puts a jump to some memory address, let's say 13, right? And the problem is that we've now removed 3 bytes, but we've put 1. So that's not we can't do that, so we just put nops here, right? Because we can only overwrite memory. We cannot, I don't know, shrink memory or whatever. And now we go to address 13, which is our newly allocated area. We just gotta allocate some memory, and we paste those instructions here. That's pretty cool. Okay, but so whenever someone calls this, it will go to here, and now we have to jump back to 5, or actually 6, so we can just edit it. This won't change anything, right? This is just, it does a different thing, right? That doesn't make sense. However, the thing is, we can jump to a random place here, and that's where we can place our hook. Let's say we have a hook function here, our hooked func, right? And this function does something else. I'll just copy some code and let's say that this is our new function that the person writing the plugin wrote. Instead, we can jump to 32. And now whenever a piece of code calls our original function, it instantly jumps to 32, which is our hooked function. Really cool. And now the hooked function, the compiler will automatically put a ret at the end, so it will return here. And suddenly, magic, this function was never called. It never happened. Now, Hyprland hooks will also give you the original pointer, which technically isn't original, but the original pointer will be pointing to this place. What that means is that the computer will start executing these few bytes that we had to yank in order to put a jump, because absolute jumps are generally pretty big, and it will continue executing as normal. Our hook was completely avoided. So if we have a plugin function, like if we have a void, I don't know, hooked is workspace visible, right? We can do, I don't know, return true, right? For example, cool. But we could also, for example, save the value of the original function, right? Bool ret equals original ID. And for example, we can check the ret. If ret equals false, for example, do some logic, right? Or return true or return ret, right? We can do whatever we want. We can not call it. We can call it and save it in a value. Whatever. Really, really cool, right? And if you go to like the official plugins, almost all of them use hooks in some way or another. Okay. this one does, yeah, damage hook. Right, for example here, on damage, this is a hooked function from within Hyprland with the signature commit subsurface, right? Cool. And now, whenever that function will be called, if some conditions are met, it just returns the original, right? Okay, it doesn't return anything, so it just calls the original, returns. But in some other states, it changes some values, then calls the original, then changes some values again, right? So we can basically do whatever we want every time that function would have been called. Now there is a problem. The biggest problem is not that, oh, we're overwriting read-only memory. We can fix that with something that is called an mprotect. But the biggest problem is that most of the code is relative. So that doesn't matter where it gets allocated, it still will work, right? So instead of using addresses like 32, we would use address jump plus 30 plus 29, right? We're on 3 plus 29, that's 32, right? And that's cool for most things. But if we're using relative addresses, then if we move code outside, that creates problems. Because what if the first instruction here didn't say add EAX2, but add EAX, I don't know, 12 of the current address, right? So RIP is a register that holds the current address of the function, or sorry, the address of the next function to be executed. So RIP, if it would be here, right, that would be 5 plus 12, that would be 17. But now that we've moved it here, that's 5 plus 15, that's 20. That's wrong, right? Because at 20 there's nothing. So what do you do? Well, the real solution is to either tell the compiler to not use it, which kind of sucks, or to do a very ghetto method that I do, and that is to read the assembly, find where you use the RIP, and replace it with code that is absolute. Well, since we're just patching live memory, we can get by with absolute addresses, because once our compositor shuts down, you know, we'll have to do it again when it starts up. It's not permanent, so it's fine. And we have the ability to obviously resize the memory place, because this is just something that we allocated. But it's hacky. First of all, I just patched Moff, Colin, Leah, because I haven't seen much other uses of RIP. And second is, this sucks. This kind of sucks. There's a lot of reasons. First of all, I mean, this is just playing with fire. This is playing with raw bytes. It's kind of like you get a needle, you get a hard drive, and you kind of like manually set bits on it like a caveman. This is dangerous. Second of all, it's bug prone. Third of all, it's not portable at all, because this is just x86 assembly. That's why these function hooks do not work if you compile Hyprland for a different platform than x86, because I would have to write the assembly for RISC-V, ARM, and whatnot. And I don't speak those assemblies, I don't own a computer with that assembly, and I don't want to play with Hyprland in a QEMU. And also because nobody has yet complained, I believe. Hyprland works, just plugins don't work on non-x86. Anyway, continuing. This is very dangerous. First of all, because blah blah blah, you're editing assembly, blah blah blah. But second of all, these are not technically the only things that can change. For example, we could have here a jump plus 3 or plus 4. This is dead again. This is gonna fuck up. Although thankfully I haven't seen really that happen ever. Although if you put a for loop at the beginning of a function with no locals and whatever, maybe there would be a jump. at the beginning of the function, but it's very rare, so I don't really patch it. This is horrible. You should not do it. Rust will not allow you to do it. Python will not allow you to do it. Java will technically allow you to do it, but it's terrible again. Don't. That's my advice. Don't. The only reason I do it is because it's powerful, it alleviates a lot of pain on my side, and throws it onto maintainers of plugins. And 3, because I've done it before, I know what it comes with, and I had a lot of confidence that I will make it right and it will work. And so far, it's been working. It's been working pretty well. Genuinely, if you want to read this code, feel free, but this is not very readable. This is not very readable. These are the internals of how the actual trampoline works, right? We allocate some memory with mmap. Christ. We don't, with mmap, with malloc, blah, blah, blah. Mmap, literal system call. So we're doing very, very C stuff. And one last thing that I wanted to say is that one of the things that you might encounter when you're doing this is when you're creating the trampoline, it is important that when you're overwriting these bytes, you will probably get a segmentation fault. That's what the mprotect is for. Every page that you allocate in memory, and a page is kind of like, imagine your memory as just a continuous, like list of addresses. These are not actual physical addresses on your RAM. They're just kind of like fake addresses that the operating system gives you. And they're ordered into pages. A page is some size, let's say 1024 bytes, right? And your system, whenever you allocate, it gives you one page or more, right? So malloc and calloc and stuff like that simplify the getting of the page, but the actual truth is that behind the scenes you get a page. You cannot have half a page of memory, right? So every page has a protection, kind of protection model flag or whatever. And just like files in Linux, it can be read, write, execute. So if a page has the protection of read, you can only read from it. If it has write, you can only write to it. And if it has execute, you can only execute. You can mix and match, right? The thing is, your code, so the actual instructions, almost always will be in read execute memory. So you can read from it, you can execute it, but you cannot write it, right? Data lives in a different page somewhere else. The reason is that you do not want to accidentally overwrite your code when your code misbehaves, right? So it's better that you instantly get a segmentation fault that you're trying to write to the wrong place, rather than overwrite some code and then later get magic happening and God knows what happened, why or where, right? It's better to instantly just get a seg fault, get a crash report, get a stack trace and fix it, rather than, deal with undefined behavior. Now, since you're trying to overwrite it, you'll get a seg fault. So you have to mprotect it. You have to change the protection of the page to allow writes. Later, you probably want to revert it, just for your own sake. But one thing that I did do wrong, which I will remind you to do if you're planning to do this yourself, you have to mprotect the entire page, and you have to do it from the start of the page. If you do it wrong, so if you try to mprotect from the middle of the page 2 bytes, it will just not work. So figure out the page size. Actually, I don't know what the page size is on Linux. Figure out where your page starts, how many pages you need, and mprotect it, and revert. That's one thing that I've had happen in Hyprland, genuinely, when a function would be allocated between the pages, right? So half of the thing that I had to yank would be on one page, half would be on another. It's no problem for the operating system, but mprotect here would only protect half of it. And when I was trying to override it, it would segfault. So that's, I believe, the last thing. Some notes here, obviously, in the beginning, I would just raw patch bytes, and some of the remnants here are still here that I literally just take like raw addresses and put garbage like here, memcopy with offsets. That kind of sucks. I've since moved for the main code to using udis. It's a disassembly library to print me the actual instructions as strings, and then I can edit the string and I can throw it into GCC. Well, technically GCC's assembler that can just assemble it, and then I just write the bytes again. So it's kind of the Unix philosophy, I would say. I'm using smaller tools that are very good at something, for example, disassembly and assembly, in order to power my bigger tool, for example, Hyprland. So that will be it for today. I hope you learned something cool about this monstrosity that I wrote that is powering almost all the plugins for Hyprland. And although I think all programmers that have ever seen this have said that this is terrible, it's been one of the best working things in Hyprland that I've ever made. All the plugin people really enjoy, putting function hooks everywhere. So yeah, I think this system is here to stay, and it's not going anywhere. So thanks for watching this, I guess, long video, and I'll see you in the next one, whenever that comes.